Welcome to Math Dog, Episode 3, Circles. When studying circles, you need your usual tools to use. A compass is handy, protractor, a straight edge. If you have a right angle, that can help. It's also not a bad idea to have little things to draw circles with. This is quicker than using a compass. Zippity zip. If you have neat handwriting, maybe a little one. If your handwriting's a little messy, you might want to use a bigger one. This is Math Dog's favorite circle to use. To set up a page for me, let's come on over and see how she did. Oh, nice work, Math Dog. Especially since you don't have a thumb. I think you get a Le Champion award for that, for sure. First, we'll draw a central angle. That's when the vertex of the angle is at the center of the circle. That's a central angle right there. We'll use this nifty protractor to measure it. It goes all the way around to 360 degrees. Let's see, this is 0. We come around to 105, 110, that's about a 112 degree angle. If the central angle is 112 degrees, then the measure of its arc, its intercepted arc, is also 112 degrees. That's always true for any central angle. For an inscribed angle, the vertex of the angle is actually on the circle. So let's see what happens here. I draw across the circle. Doesn't have to be a diameter. And I draw an angle where the vertex is on the circle. Let's measure this inscribed angle. It looks like it's about 45, 50 degrees. So if this is 50 degrees, all right, I wonder what the measure of the intercepted arc is. Well, let's put this on here and check it out. If that's at 0, then we come around here 90, 95, 100. Well, how about that? The intercepted arc is always twice the inscribed angle. That's the relationship there. Now, what's going to happen with this one? This is a sample problem that you might see. They would tell you one bit of information. Let's say you know the measure of this central angle. I already measured it. It's 100 degrees. If that's 100 degrees, the intercepted arc is also 100 degrees. And if that's the case, then the inscribed angle would be 50 degrees. At least it's supposed to be. Let's see if it really is. We'll measure it. We'll put the nifty protractor there. Lo and behold, 10, 20, 30, 40, 50 degrees. It worked. Now here's what's kind of cool about this. You don't have to use any special point here. This would work. Let's do it way over here, shall we? I could have chosen any point for my new vertex, and I'll draw a new inscribed angle here. If this is 100, then doggone it, this should also be 50. I wonder if it is. 0, 10, 20, 30, 40. If it kept on going, do you trust me? Let's see. If I were you, I don't know why I would trust me. Let's see here. 50 again. Haha. You'll see various problems. Sometimes they'll give you the central angle. Sometimes they'll give you the intercepted arc. Sometimes they'll give you the inscribed angle. Vocabulary. We have a circle. Here's the center of the circle. You name that with a capital letter because it's a point. And this is the symbol for circle. You draw a circle with a dot in the middle. Circle P, you would read that. Math Dog chose the name for that one. You can use any letter. A diameter reaches all the way across the circle. It must go through the center. Radius goes from the center out to the circle. It's always half of a diameter. The only difference between a chord and a secant is that a chord is a segment that stops on the circle. A secant is a line that keeps on going. Run wild, be free. Tangent is my favorite. Here's a tangent and another tangent. If we have two tangents, by the way, it's not the same meaning as when we were studying trigonometry. When we have two tangents, if they intercept the circle here and here, these distances, these lengths, have to be the same. I've marked them as congruent. The tangent touches the circle at just one point, and it always forms a right angle with the radius or a diameter coming across, something that goes through the center. Do you believe me that it must be a right angle? Well, I'll show you why. This table is a circle. The split down the middle would be a diameter. Here comes a tangent that touches the diameter and makes a right angle. We can see it's a right angle. Now you might say, well, couldn't we just scoot the line over and it would stop being a right angle? Well, we could, but look what happens. Now it doesn't touch the circle at this point anymore. We've moved it over. When we move it back, it must be a right angle. A tangent always forms a right angle with the radius or diameter. Here's a sample problem that you might see in which you have a circle, some information is given, and they tell you that this is a tangent line. Well, if it's a tangent, we know it forms a right angle. Let's keep that in mind. Hey, look at that. We've got a right triangle. We want to find x. Here's another thing to keep in mind. It's an easy idea, but it's also easy to forget. If this length is x, every radius is the same. They're like the spokes of a wheel. So if that's x, this is also x. Hey, we've got enough information to write an equation using the Pythagorean theorem. Legs squared plus legs squared is hypotenuse squared. Here we go. In blue, legs squared plus legs squared is hypotenuse squared. Let's make sure we square this hypotenuse correctly. Come over here. It's not x squared plus 4. No. It's x plus 2 times x plus 2. Careful there. You FOIL it out. Combine your like terms and end up with that equation in blue. Now, notice both sides have an x squared. Oh, that is nice. We like that. Subtract x squared from both sides. And now we don't have any x squares. Makes it a heck of a lot easier. Simple algebra now. Subtract that 4 from both sides. And finish off by dividing by 4. And you end up with x equals 3. Let's see if that makes sense. If x equals 3, then what kind of triangle would we have? Well, this would be 3. This would be 4. And the hypotenuse would be 5. Hey, a Pythagorean triple, 3, 4, 5. By the way, just to make sure you believe me, I drew this one to scale. This leg is actually 3. Nifty ruler, huh? This leg really is 4. And the hypotenuse, is it really 5? This one's drawn to scale, and yes, it is. Now I've drawn a circle on a piece of graph paper. X, Y grid, just like you've used quite a bit in your life. I made the radius 1 unit. I've made the center at 0, 0. How would we write the equation of this circle? Well, the center is important. We'll get to that on the third example. Right now, let's just worry about the radius. This number here is the radius squared. Now keep in mind that 1 squared is 1. So you write x squared plus y squared equals 1. Okay, let's do another one. How about this guy? Now, the center is still at 0, 0. We'll talk about that on the next example. The radius is 4. 4 squared is 16. So that's your equation. Now this time, the center of the circle is not at 0, 0. It's at 1, negative 3. X is 1, y is negative 3. Let's talk radius first. The radius is 2, so this number at the end is 4, 2 squared. Hey, look at the center in here. If the x value is 1, you say x minus 1, minus. If the y value of the center is negative 3, negative, you say plus 3. Why plus? Because it's minus this value. Here, minus 1. Here, minus negative 3. Thus, plus. Alrighty. We're going to graph one now. Hey, math dog, want to graph a circle? Okay, almost there.
Yeah, I don't know what the dog's problem is, but let's just do whatever we can to get her a quick shot of her reaching across to eat this, okay?
Let's graph this circle. We have an equation. I like to find the radius first. You take the square root of this number out at the end. Square root of 9 is 3. In all of my examples, that came out to be a whole number. That doesn't always happen. Now for the center, you come up here and you say, the center is at 2. Oh wait, no, it's at negative 2 because addition is like subtracting a negative. So negative 2, and then at 1, yes, at 1 because we're subtracting 1. Find the center first. Negative 2, 1, right, there's your center. Then count the radius of 3. 1, 2, 3. You could count in each direction. 1, 2, 3. 1, 2, 3. 1, 2, 3. Connect those as carefully as you can. You could use a compass to make it look really good. On your homework, you can usually draw it in pretty good. And there's your graph of that circle. Hooray. Hey, I'm going to give you one bit of math circle trivia to wrap this up. Let's say you're a basketball player or you occasionally go into the gymnasium. On a wooden basketball floor, they paint the key. This is the hoop. Here's your free throw line. To get this circle in just the right place, they measure carefully and they tap a nail in right at the center of the circle. Then they stretch a piece of wire, probably. They wouldn't use string because that would stretch. And you basically turn this into a compass. And you go roundy round and you draw this semicircle. Why do we care? Well, if you're a basketball player and you're shooting a free throw, you can line your feet up perfectly so that when you let go of the ball, these are your feet, the ball is directly behind that, and all you have to do is push it forward. You can improve your free throw shooting. They always putty over that hole, but you can go back and find it if you look for it before the game. Figure it out when the game starts. You know where to position your feet. That helps with circles.